Hey, hi everyone. Welcome back to another quantum hardware section. Uh, Probably today we will have like a short lecture because I'm planning like to talk about the box 7.5, the new Synchron book. It's about the fabric parallel cavity. So yeah, probably today will be the only thing I'll talk about because in the next I'm planning like to talk. Let me share the screen. I can show you in the PDF book. Hi, Baron. Welcome.
Carlos.
Yeah, I was telling people that today we will talk about this fabric parallel cavity. I think it will be shorter than the usual because it's basically this box 7.5. And yes, I'll talk about this today because the other part would be like start new thing that talk about atoms, two-level atoms. But I mean, because we'll be like different topics, so I think it's better we split into different sections. So probably the next section will be a little bit like larger than 1 hour. Yes, but so I have no slides today, so I'll start with a whiteboard. Okay. Okay, so today we talk about box 7.5, the February February. February. Okay, just to remember that we commented in the last lecture that this type of cavity, like the February parrot cavity, it's important too for realizing a large electrical field. Electric field. In a narrow band of frequencies in and in small volume, which is important because we want to do computation, right? So remember that the main problem, one of the main problems when we're using like nonlinear materials like crystals is that the susceptibilities, the effects of the nonlinearities are very small. So this is a type of technique that is used, in fact, is used to produce lasers, but we can apply here, our interest here will be like to develop a type of computation. So, and we saw like in the last lectures that the electric monochromatic electric field, the last lecture. We saw that we can represent a monochromatic electric field in the form. So what's the last equation? Now last lecture. E of R, you read in this way, is 0. So constants A, E, I, K, R. It is operators, right? The annihilation operator. Equation. This is equation 7. Okay, this is was like the last when we finish. So now today, so we are interested in the fabric parallel cavity and how you can like make large electric fields inside the cavity. So a basic component of fabric parallel cavity is a partially silvered mirror of which incident light, like E, EA, or EB. So basic component of fiber parallel cavity is a partially silver mirror of which incident light, EA or EB, is partially reflect and partially transmit. Reflected and transmit. This produce output fields that we'll call Nielsen calls EA prime, EB prime. And he could find a relation between them. They are related by the unity transform. It's basically a linear relation. E prime plus a part reflected. This is just convention, okay? But this is square root. In some use this convention here, but in some books, instead of square root of r, they put like r. Of course, they have like difference, not exactly the same r, but I mean it's just convention. And here transmitted part, transmitted, and this sign here is also a convention. We understand what it means. So, EAE. So here R is the reflectivity of the mirror, and T is the transmittivity of the mirror, where in this case here R plus T is equal to 1. Okay? Or to use like what the expression for the Nielsen-Schwann. So we can write this just A prime, EB prime, R 1 minus R 1 minus R minus the square root of it. EA EB. Okay, equation 752. Okay, so the location of the negative sign is just a convention. Okay, this negative sign. Okay, in this, what he is calling here, you have like a mirror which have activity I'll call R. If you have a incident light proportional to EA, or in the other side, you have E, this is ZB, and this is the part that was transmitted. EA prime, EB prime. Okay? This is just a figure in the. This is basically what we have in the beginning of the box 7.5. Okay, but let's try to understand the expression they give. So let's draw this other figure. So in the case of a fabric parallel cavity, it is made from two plane parallel mirrors of reflectivities R1 and R2, upon which light E in is incident from outside. It's a laser light, okay, that you send. As shown in the figure below. Okay, so if I have two plane waves, R1 and R2, I have incident light here. I'll call E in. So this light will come here. One part will be reflected. One part will be reflected. Reflected. And one part will be transmitted. And this part of transmitted will come here. I'll call this E0, initial. The initial part that was transmitted will come in this other mirror, and one part will be reflected and the other will be transmitted. Okay, and then this is back in return E1, return here. You have here E2, and so on. We call this EK. And we have one part here that will be outside, spit out. The part that will be transmitted multiple times here. Okay. And this cavity here in the text, he's saying that the size is D, but in fact, I think he means this is D over 2. At least to get his expression, I got using D over 2. You guys can check if it's who is right, but me, it will not, this will not like change anything. But in the text, he says that the size is D. But okay, I think it's wrong. It's D over 2. So inside the cavity, this means that inside the cavity, the light, like this light here, bounces back and forth. Back and forth between the two mirrors. Between the two mirrors. Such that the field acquires a phase shift exponential exponential I phi. Yeah, we'll define phi soon on each country. And this is because the light waves are heat taken as traveling with electrical fields of the form. So as you saw in the last lecture, like this E in that appears right there is something proportional to some E, some factor here called A, exponential IKR. Okay? So let's consider first the transmission properties of an empty cavity. Empty cavity for a linearly polarized light beam with vector k that's propagating parallel to the axis. That propagate parallel to the axis. Okay, so leftwards and rightwards fields the leftwards and rightwards fields inside the cavity at the left hand mirror are related by the propagation phase factor. By the propagation phase factor over 2 the cavity length. The cavity length. So what this basically is what we have in the textbook. So let's see what he try to understand what he means by this. So again, let's reproduce the figure. The two mirrors, R1, R2. Let's say that initially I have here light, incident light, that I'm represented by E in. So one part of this light will be reflected, transmitted. And I'll call here E0 R because it's right, okay? It's traveling from the right, left to right. And one part will be reflected. E reflected. And then this light come here. It found the R2 mirror, and you have another wave traveling for the left, E0 left. And here is E out. The part that was transmitted. So, okay, let's see if for the first round trip, what it happens. So in this first round trip, we have that this E0 here, that I'm calling E0 right. It will be proportional to the part that was transmitted. So I'll call here T transmitted by the mirror 1. So T1 E in. Let's see. Okay. And I could represent this as 1 minus R1 E in. And the other that's traveling for the left, E0 left. That by convention, I will call that the reflective part here will have the negative sign. Okay, so this will be a minus. Reflected this was reflected here in mirror 2. So R2. R2, but who was reflected was E0R. So E0 left is the part that was reflected from E0R. Okay? And the phase. That's I. Remember, that's proportional to I, K, R. But we are considering K. Let me write it first. R2 E0 R and a phase. A omega D over C. Where we consider that K is omega C. Okay, C is the speed of light. Okay, omega is the frequency of your E in here. So the frequency here in the E in. Okay, and because this is just you walk only you have like a round trip, right? You came here and then so this R here was the all this circuit, like the round trip. So D 2 times D over 2. So D. Okay. So this was like in the first, but this thing will be like you can have like multiples reflections because the light is here inside. You have the two mirrors parallel. So this was in the first case. So we could repeat this for a second time. Let's change the color. So again, R1, R2. So now this guy here come, it will be reflected by R1, and I'll call this, when it's reflected, E1 right. Okay, and then we'll come here, be reflected, will be E1 left. And again, we can write in the same way we did here. So E1 right is the part that was reflected. I'd like to show the other view. So it's this part that was reflected here, E0 left. So this is R1 was reflected, E0 left, which is E0 left is this guy here. So we could write this as minus R1, R2, E0 right, exponential like omega d over c. And then the same here, E1 left will be minus, by convention, R2, E1 right. And this E1 right times the phase. Is low. Times the phase. That's exponential I omega dc. Because it's this round trip. Okay? So this should be using E1 right here, put in here. So you'll find this will be R2 square root R1 is 0 right, exponential twice I omega d over c. Okay? Because I'm summing this. And you could do this for the third time. Let's do this for a third time, and we stop. So R1, R2, so this come here is E1 left, so be reflected. Let's call E2 right. And then we'll come here and be reflected E2 left. And last, let's see, just here that E2 right will be this part that was reflected in R1. So it's square root R1, E1 left. That's this part. And using this E1 left, we'll find that this will be R1, R2, E0 right, exponential twice I omega d over c. You see that this will be increasing, right? So in general, I keep going doing this. And we will find that En, right, would be something like minus the square root R1, R2 to the N exponential I N omega D D over C E 0. Okay, let's call this equation 1. And we can use like 1 to see, use equation 1 to evaluate E cavity. E cavity will be the sum, E cavity will be the sum over N of all these E's. That's Nielsen Schwang don't use like this R and left. I put here because it's simple to understand. But that's like I don't need to write the this index, this extra index here. So this is the same. This okay. This was just to we see what is happening. So using Schwang notation. Using notation. So E cavity will be the sum and 0 to infinity En, which will give us E0 plus E1 plus E2 plus so on. Okay. And if we use like this is my E2, for instance, and you use all the terms that we evaluate, inside the cavity, we have E0, that's the first, minus square root R1, R2, exponential I phi E0 plus R1, R2, exponential to I phi E0 plus the other terms. Okay? But this is just this expression here, this, that's R1, R2 is 0 exponential of this. I forgot to define phi, where phi is omega d over c. Okay, so I'm using this one, what I define like as right. I'm using this one. That's minus sign that appears in our series. So R1 square root R1 R2 is 0 exponential of phi, and is 0 that is the first in terms of E0, okay? I'm not considering terms of E in. So it's a sum in terms of E0. Well, if you guys notice, this is equation 2, equation. Note that equation 2 is a geometric series that in general is the sum and 0 to infinity a, let's call r to the n. This series here is something a 1 minus r, or r smaller than 1. Okay, this, I can write this, in fact, it's better write these ways. It's easy to see. It's low. I think I have, because I have one extra software open, and that's why it's so slow. So this E0 will be my A here, okay? So I'll write this 1 minus R1, R2, exponential I5 plus R1, R2, exponential 2 I5. Plus okay, this is equation 2. Equation 2. Okay. So if you do this, define this small r here as minus R1, R2, exponential I5, and A equal to E0, comparing this series with this expression. And if you do that, you'll see that E cavity will be E0, 1 plus R1, R2, exponential I5. That's equation 754. Okay? And we can see this, and that's why I think it's so slow. Let me show here why you guys. Sorry, here, because I'm with this software open. This is one of these softwares from mathematical, algebraic mathematical. So we can see, like I put here, this expression. Let me restart. But this is our expression of sum, this series here, okay, that I define. So this should be n, n. Okay, this is the expression, and we have the result. I hope it do, because it's so slow. Yeah. This is our result. Divide everything for square root of R1, R2. You, you have like 1 here and square root R1, R2. Okay? So this is our result here. This is equation 754. Okay, so this equation 754 is is a very important equation to us. Very important equation to us because because it shows that the February period cavity is a power it shows that the February period cavity equation system is very important equation to us because it shows that the February period cavity is a useful, let's write this way, is a useful tool for our purpose. That's to make computation, right? To make a big, have a cavity where we can increase the power of the, in this case, that we see that we can increase and we can control different from a crystal in the previous mode, like in the optical, nonlinear optical quantum computation. Here we can like manipulate the intensity of the field. Cavity is useful too for our purpose because the power in the cavity internal field can be written as a function of the input power and field frequency. Okay, we can write like P, the power in the cavity, in terms of the incident power from outside, from the left, outside the cavity. In terms, it can be evaluated in terms of the field in the cavity, square root, and the field outside. So this E cavity is the is the field after the multiple uh, bouncings of the light inside the cavity. E in is the light that came from outside, the incident light. So this we just evaluate this expression here, 754 is square root 1 minus R1 En divided this square 1 plus R1 R2 exponential I phi and divide by this En. So this is the E cavity that we just calculated. Divide by En. That's this one here. And all of these guys is the modulus square. Okay? This is square. So E cavity is this here. En is this. So you can just like cancel these two guys. And we have like equation 155. R1 divided by the modulus 1 plus exponential I phi R1 R2. Okay, because R1 is always, remember, R1 plus R plus T is equal to 1. So this is always smaller than 1. So you don't need the modulus here. So, okay, this is the expression. This is equation 755. It's interesting to us, like Nielsen Schwang, they ask in exercise. Let's see here. Exercise 7.15. This one asks us to plot this expression 755 as a function of the phi var phi for R1 equal to R2 equal to 0.9. Both mirrors with like 90% of reflectivity index. So I did this. So we need like to take this expression that you just evaluate. That's the 755. This here. And plot for R1 and R2 both equal to 0.9. That's why it's open here, my exercise 7.15. So here I just define our expression, equation 7.55. Remember that this big P here is the P cavity over P in, the incident power of the light. So this is the expression. Okay, 1 minus R1. This D here is the phi in the expression. I put just a D. This I is the complex I, and this R1 and R2. Okay, when I define here, it's defined. Okay, so R1 equal to 0.9. Okay, R2 equal to 0.9. Okay, and P, that is the Pcav over Pm, just to write the expression in terms of these numbers. Okay, and now we can plot in terms of the angle phi that I just call here d in this interval 0 to 2 pi. So this exponential here in this interval. If you do, and we see like a maximum here, that's around 10. So it's a maximum that's around 10. And note that's 10 when phi is about like 3. The interval is 0 to 2 pi. Pi is 3.14, right? So it's about pi here. The maximum is in pi. It's all this back and forth. It has some type of resonance that you have a maximum point in some position. That in this case here, for 90% of reflectivity mirrors, we have like this expression here has a maximum equal to 10. So this here for for R1 equal to R2 equal to 0.9 and phi about pi p kev p kev over e will be 10, right? 10. So p kev, it's about 10 times bigger than p in. And so we have like this advantage. So we can increase our the effect of the incident light inside this cavity. And the idea here in this to do computation is make this light interactive with the atoms that we put inside the cavity. Not today, but in the next lecture we'll study a little bit about the atoms. But the thing here, the idea here is that we can like increase the, let's say, the nonlinearity, and we have like a type of control. We can do this like experimentally. It could not do this when we have a crystal because it has its own properties, and that's the advantage here of this model. So let's just finish. So physically, it comes about because the constructive and destructive interference between the cavity field and the front surface reflected light. And on resonance, the cavity field archives a maximum value which is approximately uh, 1 over 1 minus r times the incident field times the incident field. So in the case, in the example on exercise 755, we use r about 0.9. In this expression here, 1 minus 0.9 is 1 over 0.1. That's 10, the maximum. And this is the most important. So this property is valuable for cavity QED. So in the next, we'll study like, so the idea is we put like the atom, so the light will interact with the atom. And the atom will interact with another atom, and then we can like this cascading, we can like transfer the information. That's the idea when doing computation. We're not doing computation yet. It's just in the next lecture we will study like the, the properties of two-level atoms, and then I think we start like the quantum computation. So I think for today is this. You guys have questions? So again, so we finish this today, and in the next we'll discuss like these two-level atoms. That's the following. In the box 7.6, we just to have an idea about this box. I think this in the next lecture will be this part, and then like we can start like doing computation. We define a Hamiltonian for interaction, and we have a model for quantum computing. But okay, questions? Comments? No, no comments here.
Yeah,
I got
I got a quick question. Just to reiterate, uh, in the there is a typo in the text. Is that correct? That
I think so. You mean
that's
about the
D over two.
size? Yeah, I think it's D over 2. Or
It
maybe
shouldn't
I'm
be
wrong.
D.
I mean, but it will not have. I think it's D over 2. Okay,
Okay.
I think you guys can check. I think if it's D, I would find like twice the phi would be like twice, but physically it's the same. It's not a
Okay.
big, it's not a big typo. Oh yeah, and I forgot like you have like E out and E reflected that you can like calculate
Hmm,
in the same way. Because
great.
what's important
Thank you.
to us here, I think, is E Kev. Okay, more questions? No. So I will stop like the recording now. We have like a small video. Probably in the next will be like a larger video because I think it has more. I could I should start I could start now, but because it will be like different topics, I think it's not good to mix. So let me stop here recording, and in the next we will talk about like two-level atoms and try to build like uh, put atoms inside this cavity. And when we do this, we will have like we'll be able like to do computation. Okay, let me stop here. Say bye, people from YouTube. So see you guys next Friday.